I am Dr. Prateek Jha from IIT Roorkee from Department of Chemical Engineering. I will be teaching this course on Introduction to Polymer Physics. This course should be relevant to undergrad students in physics, material science, chemical engineering, and also beginning graduate students in the same departments. In this course, I will not really discuss the chemistry aspect of polymers, that is not, I will not discuss like how to synthesize polymers and so on. What I will discuss is what are the universal features of polymers where we can take I would say a physics perspective and try to understand like what is happening inside polymer systems. So this course will have weekly assignments, and then we will have proctored exam of the course. So more on that later. So in the first couple of lectures, let me introduce you first of all, for those who have not had any course in polymers, we will cover like what is a polymer, then after that we want to know how are polymers different from other molecules, and then after that I want to know like how are polymers made. I already said that this is not a polymer chemistry course, so we will be very brief here. So we will discuss how are polymers made, and after that I will basically introduce the types and classifications of polymers. And after doing this, I want to motivate why study polymer physics. I already said that this is not a course on polymer chemistry. So what exactly we mean by polymer physics when I say that I am interested in the aspects which are physics related. So let's first look at like what is a polymer. So a polymer, if you have heard of it, polymer is a large molecule. Polymer is also called a macromolecule, and as you know, when we say something is macro, we are talking about scales which are like more than something like 1 micron. So these are objects like molecules which we can really see through like a simple microscope. If we have like other molecules like small molecules like methane or ethane or any molecules you are used to, you cannot see through any kind of a simple microscope. You need very specific more highly resolved microscopy to see that. In the case of a polymers, you can really see the molecules in most cases. However, I will differentiate between the macromolecules and polymers by saying that all macromolecules are not really polymers. So I would say the polymer is a subset of macromolecules. And what really make polymers different from other macromolecules is that you must have a repeating sequence of units. For example, if you know about polyethylene, that is the most common polymer, the polyethylene has a repeating sequence of CH2CH2. In this case, this CH2CH2 is what I will refer to as the repeating unit, and N in this case is the number of repeating units. Now, as you probably know, if the N is very small, let us say if N equal to 1 or N equal to 2, what you have is what we call alkanes, for example butane, pentane and so on. They are not polymers. On the other hand, if the N becomes slightly larger like 10 or 20, we refer to them as oligomers. We call it a polymer when N is really very high. So typically, and the terminology is not really very standard, if n is higher than 100 at least, then actually we start calling them as like polymers, and we'll see like why exactly these kind of things which have higher value of n different from those which have like a smaller value of n. So having said this, let me like briefly start telling about how are polymers different from other molecules. Okay, so we already said that it's like a large than compared to other molecules, but what is more important is it also flexible. And what do I mean by this? So think of like a rubber band, and you can really put your hands in there and then you can stretch it. Okay, if you think of a rubber band is made up of a polymer, and actually it's a cross-linked polymer, and we'll discuss about that later in the course. But this is the flexibility that we talk about. Okay, now I will give one more example, that think of like the hands of a robot and compare that to hands of a human being. If you think of a robot, and if you have seen like a robot, or if you have seen in the movies, it looks like something of this sort. So it has these hands which are like hinged together to some sort of a mechanical like fingers, and the robot can really move along the hinges that it is placed along the body. For example, if there is a hinge here, the robot can rotate his hands around that particular hinge. Similarly for the fingers and so on. So every hinge is giving it certain amount of flexibility. Now you think of like a human hand and see like how it is very different. So in the human hand we have like much more flexibility. For example, we can do these kind of movements, which for example is not possible in the case of a robot. So the reason why we are different is because the flexibility we possess is because of presence of the macromolecules, and the flexibility is really molecular in nature. What it means it is happening at a much lower length scale than compared to the robot case, where the length scales or the distances over which the hinge is placed is really very large. In our case, we can start thinking about it, and I will build on this description later. Our hinges inside the bodies are really placed very close together, and they are really at a molecular level, so our flexibility has molecular origin, and just like we are made up of macromolecules, and polymers are also macromolecules. So in their case too, the flexibility is built at a molecular level. It is start thinking about it as the hinges which are present at very, very small length scales. Okay, so that is one more difference between there. So having said these things, let me now try to elaborate that why I am saying that n has to be large. Okay, so let me go to the next slide here. We think of like small n cases. So let's say when we have a small molecule which contains only one carbon. Okay, and you know that it is the methane molecule. If you remember from high school, methane has a tetrahedron structure, which is really three-dimensional, and now you start thinking like how this particular molecule can change its conformation, like what really can change about this molecule. Of course, this entire molecule can rotate as a whole, it can translate as a whole, but if I look in terms of internal motion of these molecules, that is very few. For example, there is of course this carbon hydrogen bond, and there are 4 such bonds, but their bond lengths are more or less fixed. If you really put in a microscope there and try to measure what the bond length is, you of course need very highly resolved microscopes. You will not see much differences in the bond length. That means that this molecule's internal structure is rather fixed, and you will not see any variation in this internal structure. I would say any variation that you can really differentiate easily. Okay. Now you think of like what really happens if I have more number of carbons. So think of the next molecule, that is my ethane. So ethane now has a CH3 along with a CH3, again it is a 3-dimensional structure, but now there are 2 carbons and 2 carbons has 3 hydrogens each. Okay. And now if you know about from chemistry classes, but you can also easily see in this particular case, is there is a possibility of rotation around this particular carbon-carbon bond. Okay. And the way to see that is I will try to do a representation of these molecules looking from this particular end. So, I put my eye here and I am looking at the carbon-carbon bond. Okay. So, in that case what I will do, I will put my first carbon that I see from the right side and I put its 3 hydrogens like these, and then if I am looking from here, then the carbon behind is at the center of the circle that I have just drawn, and this also will have 3 hydrogens. So, now there is 1 carbon on top, 1 carbon just beneath it, you cannot see it in the graph, but that is given by this circle, and then we have 3 hydrogens of the front carbon and 3 hydrogens of the carbon behind it. Okay. Now, the 3 hydrogens in the front can be rotated with respect to 3 hydrogens behind it. For example, this can be in this particular configuration, but this can also be, for example, something like that, okay, where the 3 hydrogens are located for the front and back, which are rather close to each other in what we see, but basically it means they are roughly in the same plane. Okay. It can be like even closer, where you will start to see that both of them are pretty much aligned with respect to each other. So, 3 hydrogens behind and 3 hydrogens in front are pretty much in line in the same plane. This particular configuration I will refer to as an eclipsed conformation. This is what I will refer to as a staggered conformation, and this is what I will refer to as a gouge conformation. So, there are 3 possible conformations of ethane molecule. Okay. Now, it turns out that if I look at the energies of these particular conformations, then staggered happens to be the most stable one, and very rarely, I would say it never occurs that these conformations are observed because they are very less stable. Okay. But having said that, there is a possibility of 3 conformations. 2 of them has much lower energy much higher energy compared to the third one, and that is the reason why we see always the staggered conformation, right. The same story happens for the case of propane, where now we have 3 carbons, the middle one has 2 hydrogens, and then in the 2 ends we have 3 hydrogens each. Okay. So, now you can see there are 2 carbon-carbon bonds. Okay. So, we can look at either of them to look at what rotation is occurring. So, let us say if I am looking at this particular carbon, in that case my projections that I have just drawn will look something like this. So, the front one is this carbon, it is attached to a CH3 and 2 hydrogens, and the behind one has only 3 hydrogens. Okay. So, again just like I had in the case of a ethane molecule, also in the propane molecule we have possibility of 3 conformations. Again we can have an eclipsed, we can have a gouge, and we can have an staggered. It turns out just like the case of ethane, even in that case the staggered one is the most stable or has the least energy, and these conformations are again very less stable, and so they are not really observed. Okay? But again there is a possibility of 3 possible conformations. Now the story will change when I go to the butane molecules. Okay? And why I am saying this? Because if I look at a butane, and again let us say I look at this particular carbon, I want to look at the rotation around this particular carbon. Now of course the front one has a CH3 and 2 hydrogens. Now the back one also have a CH3 and 2 hydrogens. And now you can see that we do not need gouge and eclipse conformation, which can anyway be less stable. We really have 3 staggered conformation in this case. All of them are, I would say, more or less equally stable. You can see a conformation like just what I have drawn. You can see a configuration something like that. And we can also see a conformation something like this. Okay? So, I will refer to this guy as, this is called a gouge, the middle one is called trans, and then this is referred to as a gouge prime. Okay? Keep in mind that I am using the same word gouge for the earlier cases, but since these conformations are anyway never obtained, you can think of as some kind of intermediate conformations. So, I am using the same word, but it has a different meaning. In this case, these 3 are all staggered conformations, and all are, I would say, stable. And by stable I mean that trans may be slightly more stable compared to gouge and gouge prime, but more or less you can observe all these 3 states because all of them have roughly similar kinds of energy levels. Okay? So, what we have, I was able to show you is like as I start from methane, the internal structure was rather fixed, we did not have much internal motion. When we look at the ethene and propane molecules, there were possibility of 3 conformations, but only one was the most stable one. And then when I go to butane, then I have possibility of 3 rather stable conformations. We of course have many other conformations, but 3 rather stable conformations, and which all can really happen in the system. Now, if I extend the logic to, for example, molecules like pentane, hexane and so on, what you will see is there is a possibility of many possible conformations. For example, let us say I take a case of pentane molecule. Now, in the case of butane, we look at rotation around one particular carbon-carbon bond. Now, we can look at rotations around 2 carbon bonds, and what this amounts to is it will give you 3 multiplied by 3 equal to 9 staggered conformations. Okay? By that I mean that along the first carbon-carbon bond it can be trans, along the second it can be gouge, that is one, along the first it can be trans, along the next it can be trans, and so on. So, all the along the first carbon where I am looking at the rotation, first carbon carbon bond, it can be either trans gauge or gauge prime along the first CC bond, and then irrespective of what it was along the first CC bond, along the second bond it can be again trans gauge or gauge prime. Similarly, for this we can have trans gauge and gauge prime, and similarly for this we can have trans gauge and gauge prime. Okay. So, now if you think of like a pentane molecule, now we have 9 conformations. If you extend the logic, for the case of hexane we will have 27 conformations. For the case of like heptane we will have like 81 and so on. So, in general if I think of a polymer chain that is composed of say around m carbon atoms or repeating units, this will have something like 3 to the power m stable conformations. Now, you may argue that why I am saying m, why not m minus 1, because for the case of m equal to 1 we have only one conformation, but keep in mind that m is in this case is very large, right. So, in the formula even if I put like m minus 1 or m minus 2, that will not make much difference. The key point is or the main takeaway from here is that as I increase the number of carbons in the chain, the number of possible conformations increases, okay. And this is what I refer to as molecular flexibility, the point that the molecules can adopt many conformations is what I am referring to as molecular flexibility, and as I will talk more and more about this in the class, the polymers can really adopt many possible conformations, and that is why we refer to them as highly flexible. So, this is the next thing that really makes polymer different. Now, I want to elaborate on one particular point here. Why I am saying that I will look at the rotation around the carbon-carbon bond, and I will not look at the rotation around, for example, carbon-hydrogen bond in the system or something else. Why exactly we say that it can rotate around the carbon-carbon bond, and we of course agreed to that, and then we had shown that we have like many conformations. But why exactly I make that kind of a statement? And so let me elaborate on this on the next slide. So let us start thinking of like what is happening within a polymer chain and why I am saying that I can rotate around this or that. Okay. So let us say if we have for example 5 carbons, and I am numbering them in this particular case C1, C2, C3, C4 and C5. So, if I look at say this particular bond or any of these particular bonds, then these bonds are what? These bonds are really covalent bonds, right. So, and you know what a covalent bond is. So, covalent bond is formed by the overlap of electron clouds. So, if we really have to change this particular bond length, then we have to mess up with the electron clouds, okay. And that really means that this is difficult, because this bond must be strong enough, because this is formed by some kind of an electron sharing mechanism, okay. That really means that the bond lengths are almost constant. There can be possibility of small vibrations, but they are almost constant. Now, let us say if I look at this particular angle or this angle or that angle. Okay. Now, what is happening, right? So, now if you start thinking about it, there are some electron clouds overlapping here and some electron clouds overlapping there, and this angle is formed by some sort of a balance between the electron cloud overlap here and electron cloud overlap there. Okay. And now, if you know that for most molecules the bond angles are really constant, and the reason is just that these interactions between cloud are still very strong, right. So, they are of course not as strong as a covalent bond, but they are still very strong to be like flexible enough. So, for example, for a water molecule, we know that this angle is around 109 degrees. Okay. So, so even the bond angles are also, I would say, relatively less but still almost constant. But now let us say what happens between these four carbon atoms. Okay. So, what we can see here is I can keep this bond length same, and I can keep also the angle same, and I can rotate around the middle bond, and this is what we refer to as a torsion motion. Okay. So, I can apply some kind of a torsion where the angles between all the three adjacent carbons in the system will not change, the bond lengths will not change, but we can rotate around the middle carbon, right, and this is what we refer to as like a torsion thing. So, the torsion also will have certain angle, and now again by the same logic the bond length is by direct electron cloud sharing. So, it is the most I would say bonds are the most strong ones. So, bond lengths are most constant, bond angles are due to some kind of interactions between the electron clouds in the neighboring bonds, and the torsion angle is now between a higher level correlation between three electron clouds, and you can expect that this must be weaker than the bond, and this must be weaker than also the angle, right. So, the torsion angle are relatively more flexible. Okay. Now, I want you to start extending this idea and think of like what really happens if we have many carbons on the polymer chain, right. And let us say what happens between this guy and this guy here. Are their positions correlated? Okay. To look at it, we have to again go back to the bond logic. So, the first, this guy and this guy 1 and 2 are of course correlated because they have a bond in between. This guy and this guy, they are of course correlated because they have some angle in between. This guy and this guy is correlated by a lesser measure because there is a torsion angle in between, and as we keep on going the correlation remains, but it becomes smaller and smaller. So, the more I travel along the carbon chain, the more we see that the correlation between the positions of carbon atom decays. Okay. So, now you extend the logic when we have thousands of carbon atom, okay, and in most cases I would say all the cases in this course I will represent the polymer chain something of this sort, because it contains so many carbons that I cannot simply write how many carbons are there, it is just boring. So, if I look at say 2 points far off on the carbon chain. Now there are many carbons in between them. So the position of this point and position of this point is almost uncorrelated, okay, and this is what we use to start building about like polymer physics, okay. So building on this idea, and you can see like this is only a feature that we will see in the case of large molecules. This will not happen in alkanes containing 4 or 5 carbons. This will not happen even in say oligomers containing 20 carbons. They will still have like high degree of correlations. But when we have say thousands of carbon in the polymer chain, in that case beyond certain point, or if I travel certain distance along the molecule, this I will refer to as the contour. So if I start from say one end of molecule and I start following the molecule like this, at certain distances along the contour, the positions between the 2 points at certain distance from contour become like uncorrelated, okay, and that give rise to a great amount of flexibility, because since this guy doesn't depend on this guy so much, so this guy can be here, this guy can be somewhere else. So this polymer chain as a whole can be like this, it can be like that, or it can be like something else, right. So we can have many possible conformations of polymer chains because the positions of distant carbons along the chain are not really correlated. So let me just draw some random configurations. It can be like this, it can be like that, okay, and these are the kind of drawings I am doing. So it does not mean that all the points are like randomly moving or anything of that sort. If I really zoom in into the polymer chain, you will see that there is a sequence of carbons and they still have high degree of correlation at short distances along the contour. But since the number of carbons are too large, that really happens, or we really see this when we zoom in there, right. So it is locally very straight, it is locally very correlated, but the overall structure is I would say very flexible when we look at this particular polymer chain, okay. So this is like the idea that really allows us to start doing like polymer physics, because when I look at a polymer chain, when I started looking at it in the previous slides, so I was telling you about carbon chains, hydrogens and things of that sort. I was really putting a chemical structure on paper, okay, and when I came here, I am really drawing like a line, I am really making a representation with lesser regard to the chemistry and more regard to the physics, the particular aspect that the positions of 2 points distant along the contours are becoming uncorrelated. This is the idea that's where the polymer physics really begins, where we depart from the usual physical chemistry and we start talking about things which look something like what I have just drawn here, okay. Now there are a couple of points here. So I am already saying that we can have many possible conformations, and I have just already shown you some of these conformations, you can see here. Now of course all these conformations will not have the same energy, okay. In fact different conformations will have different energies, right, and the idea is that the energy gap between 2 conformations are not really very high. So by small fluctuations, something of the order of the thermal energy of the molecules, we can switch from one conformation to the other, okay. So what exactly it means, that if I know from kinetic theory of gases that every molecule or every atom in the molecule has certain kinetic energy, and this gives rise to a thermal energy equivalent of kBT. This comes from the equipartition principle. So this is what comes from this particular relation. The mean square velocity of molecules is proportional to kBT. Forget about the constants. The main point is that there is a thermal energy which is of the order of kBT. Kb is, by the way, called the Boltzmann constant, and T is my absolute temperature in Kelvin. Okay. So, this is a molecule like this is the energy that molecules really have, right. So, they keep on bumping with each other, they keep on gaining this small thermal energies or packets of energies, and if the energy gap between the two conformations are of the order of this kBT, then we can really switch from one conformation to the other very easily. Okay. Now, we will of course discuss like how do we find energies of a polymer chain and things of that sort later on in the course, but just in a very intuitive fashion, you can see here the kind of structures I have drawn, they are like looking to be like equally random, right. So, it can so happen, and I will show you in more detail, that at any given energy level or close to a particular energy, what we really have is a whole ensemble of possible conformations, right. There can be some conformations which are less probable, there can be conformations which are more probable, and then there can be some conformations which are never possible, or there can be some which are like the maximum possible and so on. So, we do not really talk about a particular conformation or some conformations of molecules, we talk about probability of conformations and at any given energy level how many conformations are really possible, right. Just because I told you that the number of conformations are going like 3 to the power m, we are talking about like really large numbers, and which allows for the physics audience, this large numbers allows us to do what is known in physics as statistical mechanics. So, whenever we are dealing with like large number of molecules, large number of entities, we make use of statistical mechanics. There are certain laws, and we will use that in this particular course. Even if you have not done that particular course, it will not be required because I will cover the basics. But the basic idea is this, that let us say when we talk about say thermodynamics, so we do not talk about a particular molecule or 10 particular molecules, we talk about an ensemble of molecules which possess a certain feature like a temperature, pressure or density, right. So, in statistical mechanics we try to build on the idea that it is not just one molecule, it has like many molecules in many possible conformations, which together give rise to some kind of an average property. For example, the pressure of a gas is not because of say one molecule of the gas, the pressure of a gas results from the collisions of molecules. The density also is not a property of one molecule, it is a property of the entire system. Similarly, when I want to apply the concepts in the case of a polymer, then we do not talk about the property of a particular conformation of polymer chain, but property of an ensemble of possible conformations at a given energy or for a given energy range that we can access using the thermal fluctuations that occur in the system. Okay, so I will conclude here, and in the next lecture I will talk about like how are polymers made and why exactly we do polymer physics. I already have given some motivation, but we will build on that in the next lecture. Okay, thank you.